Hello, everyone. Thank you for viewing this presentation. I'm excited to introduce your speaker, Julio Passi. Julio Passi has worked for Sony Electronics since 1990 and has spent the last 20 years serving as the company's Director of Corporate Product Safety. Julio is an active member of many professional organizations, including the IEEE, NFPA, the International Consumer Product Health and Safety Organization, and the International Electrotechnical Commission. He is also a member of the International Association of Arson Investigators and has been recognized as a certified fire and explosions investigator. Currently, he acts as chair of the Product Safety Working Group of the Consumer Technology Association. He has been a United States representative for TC-108 and has worked with the Hazard-Based Standard Development Team for IEC 62368 and the maintenance team for IEC 60065 International Safety Standards. In 2017, Julio received the IEC 1906 award to honor his contributions to the field. He has brought his expertise and experience to several Underwriters Laboratory Standards technical panels on topics related to the safety of consumer and professional electronics products. In addition, he has developed and provided product safety and product liability risk reduction training for the design and manufacturing staff at several companies throughout Asia.
Hello everyone, thank you for taking the time to view this presentation. The main topic for today is basic product safety for electronic products. First, I will share some definitions. Then I will touch on some of the aspects that we need to consider in order to achieve safe products. I will also talk about some of the actions we must take during the entire life of the product to ensure that it is safe. Safety starts when the product is just an idea and it continues while the product is in use and disposed of. Please note that these are my personal opinions and do not reflect the opinions of my employer. Additionally, this is a very brief introduction to product safety, and there are many other considerations. An effective product safety program continues throughout the life of the product and involves many departments and individuals in a company. This program is very basic in nature, but I believe that it's a good start for people who are just becoming involved in product safety. Now I am going to display certain definitions. It is important that we define some terms at the beginning so we can all have the same understanding of the meaning. I will give you a few moments to read, then we will continue with the presentation. What is product safety? Product safety seeks to minimize risks of personal injury or property damage. Examples of injury are cuts, burns, contusions, fractures, or even death. Property damage may be caused by heat, fire, and also by chemical reactions. It could involve damage to the structure where the product is located or items inside the structure, that being furniture, clothing, media, or other products. At what points in the life of the product you have to consider safety? You decided that creating this product is a good idea and that the product will provide benefits to the user. At the design stage, you must make certain that the product complies with all the applicable laws. Then, you consider what voluntary standards may be applicable to the product, and you must arrange for the product to be evaluated in accordance with the standards. These two steps of the process are the beginning. You must also conduct a risk analysis to verify that your product does not pose other risks not contemplated by the law or the standards. Marketing of the product is also very important. You must ensure that you do not market or advertise the product in a manner that may lead the user to face a hazardous situation. Service is another factor. You must provide the correct replacement parts. You must also advise repair personnel of the tests they must conduct after servicing the equipment. Market performance is another critical area in which to be involved from the safety point of view. The users will tell you about their experiences. You must ensure that the people communicating with the users and servicing the equipment know how to identify a potential safety issue and how to report it to the appropriate person in the organization. This person must be responsible to analyze the report and act accordingly. Safety process. Achieving safe products is a 4-step process. We identify hazards and determine the risk by performing a risk analysis. We may use our knowledge and experience as well as a number of tools available to us. Proper use of these tools will enable us to identify most of the hazards, if not all. The priority is to eliminate the hazards during the design of the product. By designing the hazards out, we eliminate the possibility of harm. If hazards cannot be eliminated, we will implement safeguards. If any hazards remain, we will provide adequate warnings and instructions in how to safely use the product. What is risk analysis? Is there an app for that? That would really make it easy. We can just make the risk disappear. But it's not that easy, so let's talk about risk analysis. Sometimes we hear risk analysis and think that it is a very complicated task. However, we perform risk analysis every day, even many times a day. I'll give you an example. While driving, we perform many risk analyses. When changing lanes, when reaching a stop sign, when making a turn, and many other situations. In the case of electronic products, we will look at the risk while the product is being operated and also while it is not being operated. We must also analyze risks that may appear under abnormal operating conditions and also under unreasonable and foreseeable misuse. Keyword being reasonable, a word that has a legal definition. This photo represents a situation in which you must conduct a risk analysis. We arrive at the intersection and have a few choices: go straight, turn, or stop and look. If we choose to stop and look, that is a risk analysis. The road is clear, then we proceed. Right now is a very bright day. We can clearly see. But what happens next time we get to this intersection? Now it's the evening, and we don't see as clearly. In an analogy, can we compare this to an abnormal condition? Different users may have different challenges. We must take those into consideration also. Third situation. The intersection is now a four-way stop. You didn't know this area, so you are really paying attention. However, other drivers in the area might be used to the old way. It is possible that the driver coming at the intersection is distracted and does not see the just installed stop sign. The driver might continue through the intersection and hit us. Can we think of that situation as reasonable and foreseeable misuse? Risk analysis process is not the task of just one person. Ideally, you should engage a team. At a minimum, you should have the following people in your team. Naturally, the design engineers and product safety experts. The engineers know everything about the product and can answer questions from the safety experts and implement their suggestions. Attorneys and compliance experts will ensure that the product meets the legal considerations and the warnings and instructions are effective. Additionally, you may want to consider human factor experts to help you see ways in which your product may be used, especially when you're introducing a totally new product. There are several tools available to help us place safe products in the market. I will mention just a few. By doing some research, I'm sure you can find some that will meet your needs. IEC 62368-1 is the most up-to-date safety standard for audio-video products. As such, it is a very valuable tool, Meeting the requirements of this standard is a major step in achieving safe products. The standard is an international safety standard. It is a collaborative effort for which several people and companies from around the world have committed their time, expertise, and resources to the project. Experts from a diverse background and disciplines have analyzed risks associated with the products, thought about ways to mitigate those risks, and written requirements to ensure safe products. Countries may adopt the text of the standard as it is, or they may include national deviations. UL 62368-1, published by Underwriters Laboratories, is a United States version of the standard. It is worth mentioning that UL 62368-1 is an American National Standards Institute, or ANSI, approved standard. Here you see the Canadian version. It should be noted that it's harmonized with the US version to facilitate compliance. There are also some other documents which contain helpful information, such as CENELEC Guide 29, CENELEC Guide 32, and IEC Guide 50. Another tool is the risk assessment chart. If you are looking for a visual representation of risks, this chart could be the answer. You could use one axis for the probability and the other for the severity of the harm. Going back to our definitions, safety is freedom from unacceptable risk. As such, once you assign a number to the risk based on these two factors, you can quantify risk. How to determine possibility of harm? I mentioned before IEC 62368, the safety standard applicable to our products. To determine the possibility of harm, we are going to use the three-block model from IEC 62368. Let's review the basic model for harm. We have an energy source, could be heat, radiation, mechanical, electric, or any other form of energy. Then we have a body part or a combustible material. Combustible materials could have many forms. Now comes the transfer mechanism. Could be any of the three shown here. If the path is completed, harm may occur. It could be in the form of pain and or injury to a person, or ignition or other type of damage to materials. Are all energy sources likely to cause harm? It depends. It depends on the energy level and the time of exposure. First, we need to answer the question, is the source capable of releasing enough energy to cause harm? If the answer is yes, then we determine the typical time of exposure to that energy source. If you look at Table 38 of IEC 62368, you will see this method in detail. The harm could vary greatly depending on the available energy and the length of the exposure of that energy to the body part or combustible material. Let's analyze an example of that concept. We will see an example of how the same energy source can have different effects in the same material, just based on the amount of energy release. A match with an energy release of only 50 watts can easily ignite the toothpicks. However, it cannot ignite the fireplace log as much more energy is needed. To continue analyzing the concept, we will see an example of how the same energy source can have a different effect based on the length of the exposure. We can ignite the toothpicks if the time of exposure to the flame is long enough. However, a very short time of exposure will not cause ignition. Identifying hazardous levels. We've seen that the first step in the process is to identify the hazards. To properly identify the hazards, we must quantify the energy sources of the product. But how do we know which levels of energy can cause harm? I mentioned that there are tools available to us. One of the tools mentioned was IEC 62368. This standard helps us quantify the energy levels and as a result determine the hazardous level. IC 62368 classifies the energy sources in 3 levels, as shown here in the slide. They are called Class 1, 2, and 3. Also shown here is the effect on the body and combustible materials or the different energy levels. So now we will see some forms of energy related to electronic products that we consider capable of causing harm. Electrical energy, thermal energy. Thermal energy is the result in our products of electric current circulating through a resisting medium, typically conductors, semiconductors, and resistors. Mechanical energy. An example to consider is moving parts. More forms of energy. Kinetic energy, the energy of an object in motion, for example, a falling product. Chemical energy. Chemical energy is a type of potential energy. A chemical reaction will generate another type of energy. One example is a battery, where a chemical reaction will generate electricity. Radiated energy is the energy that travels by waves or particles. We will see a few examples in the next slide. First, we see acoustic energy. In our products is typically generated by headphones and speakers. RF energy, the energy generated by transmitters, Wi-Fi, Bluetooth, and mobile phones. Optical energy, from high-power lamps, such as those in image projectors and also laser. Avoiding harm. We learned about the 3-block model before. Let's use it now to see how we can avoid harm. We also saw how important the level of the energy source is. Therefore, one method we can use is to reduce the level of the energy source. Then we do not have to consider the transfer mechanism. If we cannot reduce the energy level, then we can interpose a safeguard. The safeguard will disable energy transfer from the source to the body part or combustible material. In the next 2 slides, we will see some of the hazards that the energy sources may pose under the right conditions. Electric shock, fire, burns, and physical injury. Now we look at some more hazards: chemical, choking, and radiation. Electric shock model. Electric shock occurs when a body part becomes in contact with a conductive and energized part of the equipment. The effects of the electricity in the human body depend on factors such as the voltage, internal impedance of the source, and whether the source is DC or AC, and its frequency. So what are the effects of those electric shock? Here we see those effects that electric shock may have, from just a sensation to grave injury or death. Fire hazard. Effects of fire. The effects of fires are personal injuries such as burn of smoke inhalation, also property damage, which may have a wide range. Burn hazard. Since heat generation is generally not the main purpose of our product, thermal injuries are not highly likely to occur. However, we must consider long-term exposure and product malfunction. Burns effects. Burns injuries are classified by degree. I'm sure you all heard the terms first, second, and third degree burns. What does that mean? It means how deep the damage caused to the body part is. You see on the screen a representation of the depth of damage, being 4th degree the greatest damage to the body. How do we determine that there is risk of burn injury? Based on safety standards. Depending on the type of product, we may use IEC 62368 or other standards, we must take into account the temperature of the area, the likelihood of contact, the material, and the length of contact with the heated surface. Then we will determine the appropriate safeguard if one is needed. ASTM C1055 and ASTM 1057 are other standards to be taken into account as they consider not only temperature, but also the length of exposure to the heated surface and energy transfer. Let us now discuss mechanical hazards and their effects. First, we see stability of the product. This is essential for products that are located where children could be present. The majority of consumer electronic products fall in this category. Second, we see moving parts and their effect. Finally, sharp edges, especially important in products with metal enclosures. We have also to be mindful about protruding fasteners, such as screws. Chemical hazards. There are laws and regulations that apply to chemical hazard. Two that I can mention for the USA are the Federal Hazardous Substance Act and the Consumer Product Safety Improvement Act. Both address banned substances and substances requiring labeling. I recommend that you research and follow the applicable laws and regulations. Radiation hazards. Let us now review the effects of the radiation hazards and how can we limit their effect on the human body. High levels of acoustic energy may cause hearing damage. There are safe limits established by the standards and in some countries by the law. Laser and high-intensity lamps may cause ocular damage. To reduce risk, laser power is regulated in the USA by the Food and Drug Administration, or FDA. In venues where lasers are used, in order to eliminate exposure, the beams are projected outside the area where the attendants may be located. RF exposure, for example from mobile phones, in the USA, exposure levels are regulated by the Federal Communications Commission, or FCC. Choking hazard is a risk specific to children 3 years old and under. It involves small parts that are easily removed from the equipment and that fit in the test cylinder. The test cylinder is used to determine if a part may pose a choking hazard. Small batteries, such as coin type or bottom cell, have been found to be dangerous when accessible to children. Children may swallow those batteries, or they may insert them in their nose or ears. If the battery becomes lodged in the esophagus, it will cause a grave injury, sometimes fatal. Bottom batteries are more likely to be inserted in the nose or ears, causing all significant injuries. The coin cell batteries are difficult to identify as they may look like a coin in the X-ray. We see here the X-ray of a child who swallowed a coin cell type battery. In this case, we can identify that it is a battery and not a coin, but if it was reversed, the doctor may confuse it with a coin. Batteries should be removed immediately, as they can cause irreversible damage in less than 2 hours. What is next? We've done a risk analysis and identify all the hazards associated with the product. Next step is to eliminate those hazards at the design stage. Let's discuss some of the measures we can implement to achieve this goal. At the electrical design phase, we must examine the circuit to identify the critical components. We must ensure that these components are suitable for the specific application, for example, the correct rating fuse, and that the components we use are tested for adequate performance in accordance with the corresponding component standard. Other design considerations: insulations, materials, and physical layout. Regarding the internal construction, we must ensure that we use adequate materials and that those materials are suitable for the application, the spec of use of the equipment, and the environmental conditions to which it may be subject. We will see 3 examples of those considerations. First, we notice that the printed circuit board is classified as V0. What that means is that the material is fire resistant. In the next example, we see that the creepage distance has been increased by incorporating a gap in the PC board in order to avoid arcing. Lastly, we see that the components that, under abnormal operating conditions, may achieve elevated temperatures have been separated from the PC board to prevent ignition. These are all examples of safeguards incorporated in the design of the product. The external construction of the equipment is also very important. We must ensure the stability of the product. Depending on its weight, the potential and kinetic energies could be capable of causing injuries, particularly to children. We know that some products will be dropped. Do they remain safe after dropping? Damage to the product may result in detached small parts that a child may swallow. It may also result in exposed energized areas or hot parts. Accessibility to energized areas is also a concern. We see here a subwoofer, for example. Typically, this product is placed on the floor and easily accessible to children. It is possible that a child punctures the speaker with a metal object. Could internal energized areas become accessible then? We must ensure that we implement barriers which will prevent contact with energized parts. What is next? We've done a risk analysis, and we identify all the hazards associated with the product. We also endeavor to eliminate those hazards at the design stage. For the remaining risk, if any, we must analyze those risks and incorporate adequate safeguards. Let's discuss some of the measures we can implement to achieve this goal. Safeguards. We look at the hazards and thought about the probability of those hazards causing harm. Then we work to eliminate those hazards during the design, and we are left with some hazards that cannot be eliminated. We see here that if we want to use a fireplace, we cannot eliminate heat. That is its purpose. In order to limit the hazard, we interpose a safeguard. As an example, in the case of an electronic product, sometimes we cannot eliminate the risk of electric shock. Some of the products are energized by the mains, and the voltage is considered dangerous. So what do? We incorporate safeguards. For example, the equipment enclosure. The main purpose of the enclosure is to insulate. It insulates from energized parts, hot parts, and mechanical hazards. Safeguards considerations. When deciding on the safeguard, we must consider who is going to be exposed to that energy source. It's a quite different situation if the person exposed is an engineer, or a person properly trained to safely handle energy sources, or a child. Types of safeguards. Next, we will see three types of safeguards. First, equipment safeguards. They are safeguards implemented in the equipment, for example, enclosures, insulation, etc. Next, we see installation safeguards. These are the safeguards that are part of the structure and equipment. For example, proper voltage supply, protective earthing, adequate supporting surfaces. Finally, we see instructional safeguards. They are symbols and or words which indicate a potential hazard and how to avoid it. These safeguards could be attached to the equipment in the form of a label or provided with collateral material. Electric shock safeguards. For safeguards against electric shock, we employ insulation. Here are some types of insulation. In addition, we can implement proper grounding of the equipment. Fire risk safeguards. As we discussed before, limiting the power is always an option. Material choice is very important. Can we use plastic, or is metal the best choice? We may increase the distance between potential ignition sources and combustible material, or incorporate fire enclosures. Sometimes the proper solution is to use two or more methods. Burn risk safeguards. If possible, limit the temperature of the accessible part, for example by increasing the distance from the heat source. You may choose a material with less efficient energy transfer, or you can prevent accessibility by insulating the hot part. Radiation hazard safeguards. As usual, reduce the available power for some pressure or change the laser class. Comply with the regulations, the FCC, FDA, and voluntary standards. What's next? We completed step 1 of the process, then step 2, then step 3. Now we determine that some instructional safeguards are needed. Let's review the process for implementing instructional safeguards. Now we will spend some time exploring instructional safeguards, or warnings and instructions, as they are known in the United States. Instructional safeguards are the least desirable option. They are not as reliable as other safeguards as they depend on the user's behavior. We mentioned the safeguard must consider the audience. This requirement also applies to instructional safeguards. Here we see an instructional safeguard for an ordinary person, and now a safeguard for an skilled person. These are both instructional safeguards, but for different audiences. We will now review which standards apply to instructional safeguards. When the only choice left is to incorporate instructional safeguards, we must refer to the applicable standard. First, we will review the product standard. What are the required instructions specified in the product standard? We will incorporate those. If we determine that due to the characteristics of the product and expected use, other instructions are required, we will refer to ANSI C535 for the language and format. Instructional safeguard must include a specific element. They are the alert symbol, the signal word, could be one of those, 3 choices depending on the situation. Then the adequate colors. I should mention that color is not mandatory, and that if color is not used, the standard also specifies the proper level of gray corresponding to each color. Another element of the instructional safeguard is the text. It must clearly identify the hazard, then how to avoid the hazard. Later, we will see the process we must use to develop this instruction that we see on the screen. C535 language. It is important to use the correct language to deliver the message. We do not want the user to disregard the message or to be unnecessarily alarmed. The signal word must be consistent with the risk, and the message must be clear and concise. It must specify the risk, how to avoid it, and the results of not hitting the warning. We do not have to use color, as I mentioned, but if we do, we must follow the standard. It is not just any red or yellow. The exact color is specified in one of the standards of the series. I will now display the conditions under which of these signal words shall be used. I will give you a moment to read. I'm sure you have noticed that sometimes I use warning and other times I use instructional safeguards. I am not trying to confuse you. The intent is that you become used to the term from IEC 62368. We know that warnings is the most widely used in the USA. How to develop an instructional safeguard. Next, we are going to analyze an example. This safeguard in the form of a label is attached to the core of a nursery monitor. In the past, there have been reports regarding children's death involving this type of product. Concerned parents, trying to ensure that they could hear the baby, sometimes place the nursery monitors directly on the crib. Unfortunately, babies move around and may become entangled with the core of the product. In some cases, this has resulted in strangulation. The industry, in cooperation with the CPSC, developed an ASTM standard and adequate warnings for the parents and caretakers. Here we see 3 different instructional safeguards. Which one is correct? I will give you a moment to think about it, then we will go through the decision process. Here we see our 3 choices. We will analyze them one by one. First, danger. If we place the product on the crib, is death or serious injury certain? No. We can eliminate this one. Second, warning. Is death or serious injury possible? Our experience indicates that it is. Then this is a possibility. But let's see about the next choice. Finally, we see caution. The key words are minor or moderate injury. But we already determined that death or serious injury is possible. Then the correct choice is warning. Here we see the complete label to be attached to the core. Why do we attach it to the core? It is more likely to be seen and therefore more effective. What's next? Next, we can start the whole process again to ensure that we did not miss anything. Also to see if another risk was introduced as a result of the safeguard or warning. I understand that we went through a lot of information. If there are only 2 things you will remember, they are: follow the laws and regulations, use the safety standards and guidelines available to you. Remember and follow the 4-step process. It is the key to success in achieving product safety. Number 1, risk analysis. Number 2, eliminate risk during design. Number 3, implement safeguards. Number 4, if necessary, incorporate appropriate warnings and instructions, or instructional safeguards as they are called in IEC 62368. We have reached the end of the program. Once again, thank you very much for your time. I hope that you found it time well spent and that you have learned something new. Now is the time for questions. Thanks again for your time.